Okay, couple of reminders. Lab that we did yesterday, guys. That is due on Wednesday. Yeah, it's April 2nd. Okay, so if you're wanting me to look over that, or you want some feedback on it, or anything like that, make sure you pop in and see me before then. Okay, also a reminder that your quiz this Friday is going to be on Newton's second law. So practice quizzes 1 through 5, okay, are going to be the ones that are important. Okay, have a look at those, watch the videos, come in and get some help if you have any questions on any of those. Okay, but we've basically covered everything about Newton's second law that we need to cover at this point. Okay, friction kind of goes with both Newton's second law, but also a little bit with Newton's third law, which we're going to talk about next week. But we can do the friction stuff for right now. Okay, so anytime two surfaces are in contact with each other, there's going to be friction. Okay, two things are going to affect how much friction there is. Okay? What two things? What two things might affect how much friction there is?
Texture.
Yeah, actually, texture is kind of part of it. The nature of the two surfaces. Okay? The nature of the two surfaces is what we call the coefficient of friction, which we use mu to symbolize. Okay? What else? Weight. Yeah. How, or in the absence of weight, at least, how hard are the two surfaces being pushed together? Okay? The harder the two surfaces are pushed together, the harder it's going to be to slide them past each other. All right? And I can't remember if it was you guys or period 4 that I did this demo with the other day, okay, where I picked up the desk and pulled it towards me and it moved very, very easily. Was that you guys or period 4? That was you? Okay. Versus if I lean on it and try and push it forwards, it won't even move. Okay. It's the same two surfaces. It's the little tennis ball things on the floor. Okay. But suddenly it's nearly impossible, or is impossible, for me to move the desk. Well, all that's changed is the normal force. Okay. When I lift up this desk, most of the weight of the desk is now on my arms. I don't have to worry about it pushing the two surfaces together, right? Gravity is still pulling on this desk with its normal weight, but I'm not letting all of that weight rest on the floor. Okay, so normal force and gravity aren't equal in this situation because I'm bearing some of the weight. Everyone okay with that idea? But if I go to this situation and I push down on the desk, now normal force and gravity are also not equal. Normal force is bigger, because it's not just the weight of the desk, now it's also my weight. I'm adding to it, okay? I'm pushing that desk harder into the floor than it does in this situation, all right? If normal force goes up, then it's harder to move the desk, okay? Because the force of friction is calculated by taking the coefficient of friction, mu, and multiplying it by the normal force involved in that situation. Okay, this is why, if you have a pickup truck, you probably put weight in the back of it in the winter. Okay, I throw about 200 pounds worth of weight in the box of the truck, okay, that we have, so that I have better traction in the wintertime over the back wheels, because if I don't, and the box is empty, I have very poor traction over the back wheels. Okay? Simply increasing the weight over those back wheels increases how hard the ground has to push back and increases my force of friction. Okay, does that sort of make sense to everybody? Okay. All right, so friction is dependent on basically those two things. There are also two kinds of friction. There's static friction and kinetic friction. Now, kinetic usually means the object's doing what? Moving. So kinetic friction is the friction possessed by objects that are actually sliding past each other. Static friction means the objects are not sliding past each other. The friction is there, the forces are there, but there's no movement happening. So in a situation involving static friction, what's our net force? 0. Okay, so in this situation here where I'm pushing on the desk and it's not moving, this is a static friction situation. All the forces are balanced because the desk's not going anywhere. Okay, this is a kinetic friction situation. Now the surfaces are sliding past each other. Okay, the object did accelerate towards me. Everybody okay with the difference there? Okay. Which is better? Which do you want to have if you're, let's say, it's really icy and you're trying to get out of the parking lot? Which one do you want to use?
Static.
Static. If your wheels spin, you could actually go backwards, even if they're spinning forwards. Okay, you can slide back down the hill. People have done it. Okay, we've seen it happen. Okay, it's why you shouldn't get too close behind somebody, especially when it's icy. All right? Static friction is always greater than kinetic friction. Okay, so if you had the same two surfaces, the coefficient of kinetic friction will always be smaller than the coefficient of static friction. Okay, we're not going to deal with like two separate charts or anything like that, just as long as you understand the difference. Static friction is what's more desirable. It's why modern vehicles have all sorts of traction control systems and things like that to prevent the tires from spinning. Okay, the same is true for anti-lock brakes. Okay, what's the purpose of having anti-lock brakes? Why are they safer than like old school where you just slam on the brakes and leave tire tracks? What can you do with anti-lock brakes that you can't do if you're skidding?
Smash beside the gear of your brake and see how walk around.
Well, no, you can. If I slam on the brakes, I mean,
You lock your tires on
you can lock your tires up. So what can't you do with kinetic friction? The whole reason for having anti-lock brakes is to allow you to steer while you are slowing down. Being able to steer requires your tires to be rolling. If your tires lock, you are going to go straight. You will not be able to steer. Okay? Steering requires you to be able to turn the wheels and have them roll to exert a force in that direction. If your tires are locked, all you will do is obey Newton's first law. Okay? You will go nice and straight, okay, into whatever it is you're trying to avoid. Okay? Everyone kind of follow me on that one? Okay, so we want to rely on static friction as much as possible because it's greater and allows us to do things like steer, okay, which is kind of important. Okay? All right. So friction can cause, obviously, wear and tear as well. Okay, there's lots of situations where we'd like to minimize friction. Okay, if we're talking about inside of the engine of your car, for example, we would like to have minimal friction there so that the metal parts don't wear down and the engine doesn't break down eventually. Okay, how do we do that?
Lubricants.
Lubricants, yeah, oil. Okay, different kinds of oil. Modern oils are very different than conventional older oils. Okay, they lubricate. They stay more like liquid at lower temperatures. They stay more liquid at higher temperatures. They're just chemically enhanced. Okay, over older ones. Okay, that's important. The easier they can slide past each other, the better. Now, what happens to your engine parts as they heat up? They expand. Okay, as they expand, does that increase the amount of friction? Yeah, if they expand, okay, like inside of your engine, right, you've got the cylinder that's moving, or the piston that's moving up and down inside the cylinder. If that piston and the cylinder both expand, they squeeze on each other. Okay, if it gets overheated, the amount of friction inside goes way up, even if your oil is fine. Okay, and they'll eventually get to a point where they can't slide past each other anymore, and your engine will seize, or pieces will fly out. That's generally bad. Okay, so all of those things are the direct result of what we were just talking about. If those engine parts expand, the force between them increases. That increases friction. All right. So to determine the force of friction acting on an object, you need to imagine which direction the object would go if friction wasn't there. Okay, so when I push on this desk and the desk doesn't move, which way is friction acting? Forward or backward? Is friction the thing preventing this thing from moving? Okay, I'm pushing that way. So friction's got to be pushing against me. Okay? Friction is always going to act opposite the direction that it's either going or, in the case of static friction, would go. Okay? The woodpecker is back. Stupid woodpecker. Okay. He's not a very bright woodpecker. He's hitting metal. Probably concussing himself and getting dumber every single time. Okay. Everyone okay with that idea there? Not the woodpecker, but the friction part? Okay. Sorry, I got distracted. Shiny thing. Squirrel. Okay, so static friction, like we said, okay, static friction is going to result if the objects are not physically sliding past one another. Okay, so if we're looking at a horizontal surface, okay, if something was being pushed this direction, okay, then friction would act here. Okay, this would be our applied force. Okay, friction would act back this way, and then it would be related to the normal force acting on that object, which may or may not be equal to the force of gravity. Probably in most cases it would be. Okay, and the nature of the two surfaces. Okay, how sticky are they? Right? If we were looking at like Teflon and ice, that's something that would have a very low coefficient of friction. Those two things would slide past each other very, very easily. Okay. All right, so this is what I was just doing a minute ago, okay? Pushing on the desk, right? Desk didn't move. Now, there's some vector stuff related to this, right? I wasn't pushing straight forward, I was pushing down and forward. So this was my applied force right here. Okay, that applied force had a forward component, which was trying to move the desk that direction, and a vertical component that was downwards. Okay, so if I'm looking at this desk from a free body diagram kind of point of view here, I would have the horizontal, they call it Fx, I think there, right? Or F applied x. So this would be the x component, okay, going that way. And then I would have the y component. Okay, what else would be acting down? Gravity, yeah, the weight of the desk, right? And then this would be the force of friction. Okay, but I should have made it longer. Okay, what force am I missing? What force am I missing? Should be pointing up. Normal force. Now, force of friction and the force applied horizontal, how are they related? Desk's not moving. How are they related? They're equal. Okay? The net force is 0 here, right? The desk isn't moving at all. So these two forces are equal but opposite, and normal force would be the sum of these two forces, because the desk also isn't moving vertically. Okay, so if I knew that much, okay, I'd be able to calculate what the force of friction was. Okay, because I would know what the normal force is, and they would have probably told me what the coefficient of friction was. Okay, everybody all right with that? So this is really just a Newton's second law kind of problem with some vectors. We just do the analysis. All we're adding in is that you now might be asked to calculate the force of friction using this idea instead of as one of the forces in a vector sum of all forces situation. Okay? All right. Everybody okay with that situation? Static friction. Okay. If this thing starts to slide, do any of my numbers change? If it starts to accelerate forwards, all the vertical stuff stays exactly the same. That's not going to change. But if it's starting to accelerate forwards, that means this force and this force are no longer equal. Okay? It's now kinetic friction, and it's not as large as this. That's why the desk starts to slide. Okay. Yeah, okay, we just talked about that, so we're all right. Okay, I want you to copy this one down, and then I'll talk to you about it, okay? And I'll see if you can solve it. Just copy the picture for right now. Okay, I have placed this 10-kilogram block on this ramp, and it didn't move. Okay, I set it on that ramp, and it did not slide. Calculate for me the force of friction in that situation. Okay? This doesn't require any of what I just taught you. This is, right now, strictly a Newton's second law question. Okay, I put a 10-kilogram block on this 20-degree incline, and it did not move. Calculate the force of friction acting on the block. Okay, so we've done a whole bunch like this already, because it's just an inclined plane question for right now. Okay, the way I asked you, I said calculate the force of friction. That's just an inclined plane question. Right? What's the net force in this situation? It's not moving, the net force is 0. Okay, that means that F parallel and the force of friction are equal, because the box isn't moving, and those are the only two forces that would cause it to move up or down the plane. So, do my usual inclined plane stuff here. Okay, Fg is going to be 98.1 newtons. Okay, this side here is going to be normal force, and this side here is F parallel, same as in every other one we've ever done. Okay, 20-degree angle there. So I'm going to calculate F parallel. F parallel will be the sine of 20, because it's the opposite side, times 98.1. What does that come out to, guys? I forgot to start my calculator. $33. Okay, newtons. All right, so is that then my force of friction? It is, as long as I write up the ramp. Because friction's acting up the ramp, right? If I ask you what's the force of friction, I need magnitude and direction for a vector quantity. Okay, so that's just a Newton's second law question. It's just an inclined plane. Here's the new friction detail that could come in. Rather than asking you what's the force of friction, I might ask you, what is the coefficient of friction between the box and the incline? Okay, so now that's going to require you to use this formula. Mu times normal force equals friction. Okay, remember how I said in most situations we'll never use that other side of the triangle? This is the situation where you have to use the other side of that triangle that we have never used. If I'm going to calculate what mu is, I need to know what the normal force is in this situation. Okay? So, can I calculate this side if I know the hypotenuse and the angle? Okay, so normal force is the adjacent side. So just like if I'm calculating F parallel, I just use cos instead. Oh, 98.1. Okay, so my F normal is going to be 92.18 newtons. All right, now I can calculate mu because I already calculated the force of friction. It was F parallel. Okay, so force of friction divided by the normal force. Okay, so I'm going to have 33.55, okay, divided by 92.18. Okay, So my coefficient of friction is 0.36. What are my units for that? What was on the top of that equation? Right? I divided force of friction by normal force. Is that newtons divided by newtons? What does that leave me? Nothing. Coefficient of friction is just that. It's a coefficient. It tells you basically the percentage of the normal force that's converted to friction. 36% in this case. Okay? It's just a coefficient between the two. Right? Everybody okay with that idea? So it doesn't have any units. That's going to really throw you, hopefully. You'll like really want to put units on it and have to fight the urge to put units on it. It actually doesn't have any units because to get it, we divide one force by another force and the newtons cancel. Okay? Everybody all right with how that one works? Okay. Okay. Try this one. 20 kilogram box on a 25-degree incline. Okay, it is being pulled up the ramp with 120 newtons worth of force. And the coefficient of friction between the box and the ramp is 0.125. I would like the acceleration of the box. It's still mostly an inclined plane question. You're just going to have to use the new friction formula in here as well. Okay, so I'll put that up just in case anyone forgot. So, forces acting here. Obviously our applied force up the ramp of 120 newtons. Okay, since the box is moving up the ramp, that means friction is acting down the ramp, and we know it's present because they told us it is with giving us the coefficient of friction, plus F parallel. That's always there. As soon as you put something on an incline, gravity is trying to pull it downwards. All right, so we would have to calculate that force as well. All right, so first thing we got to do is calculate Fg. 20 times 9.81 is going to be 196.2 newtons. Okay, we'll have our triangle here. Okay, this angle is 25 degrees. That side's going to be F normal. That side's going to be F parallel. And for this one, I'll need to calculate them both. Okay, it doesn't really change a whole lot about what we do here. It's still an inclined plane. I just have to calculate another force. Right, so to get my F parallel, same as always, sine of 25 times 196.2 newtons. Okay, so F parallel is going to be 82.92 newtons. Right? F normal is going to be the cos of 25 times 196.2. Okay, 177.82. All right, now that I have that, now I can calculate the force of friction. Okay, mu times normal force. And I know both of those numbers, 0.125 times 177.82. All right, so the force of friction is 22.23 newtons. All right, now I've got all my forces. Now what do I do? Actually, what do I do? Right, I got to find the net force. So vector sum of all forces. Okay, so F net will be 120 newtons minus 22.23 minus 82.92. Okay, so 120 minus that number minus that number. All right, so I have a pretty small net force. Okay, the net force is only 14.86 newtons. All up the ramp. Okay, can I get the acceleration now? Same two steps, sum of all forces, mass times acceleration. All we're doing is throwing in one other little formula here. As long as you understand that relationship between normal force and the coefficient of friction, okay, and force of friction, then you're good. All right, so we'll take our acceleration, 14.86, divided by the 20 kilograms. All right, so acceleration of that box should be, to two significant digits, 0.74 meters per second squared up the ramp. Okay, that would be a pretty typical friction question. Okay, if I was going to make an inclined plane about friction, that would be a pretty typical inclined plane involving coefficient of friction type of question. Okay, now where friction questions get a little more involved is when we start having situations like the one I demoed here, where if I lift this a little bit, I'm pulling it at an angle. Okay, does that bring in some vector stuff about my forces? Okay. Okay, I'm just going to make one up here that is like this. Okay, copy this one down. So this would be a more vector related type of friction question. Okay, so I have a 25 kilogram object on a level surface. Okay, the coefficient of friction between this box and the surface is going to be 0.115. The object is being pulled at an angle of, let's say, 15 degrees. Okay. And we'll say that the force being used here would be 35 newtons. I'd like the acceleration of the box. Okay? It's being pulled at an angle, but it's moving along the surface. Okay? And there is friction there. Free body diagram is going to be crucial here. Identify all your forces, and my suggestion would also be see if you can break this force into its X and Y components. That'll make it easier to use. Okay? We know the box is moving horizontally. It's not going that way. That's kind of the key. I'll give you a few minutes to think about that when I work on it. Okay, I'm just going to identify a few more of the forces here, and then in case you're stuck, you can try and go from there. All right, so first thing we want to do is break the 35 into its horizontal and vertical components. Okay, so to get the horizontal component, we're going to go cos of 15 times 35. All right, so the horizontal component's 33.81 newtons. Okay, and that's just acting horizontally, right? Then I'm going to want the vertical component, okay? So that's going to be the sine of 15 times 35. All right, so the vertical component of that is 9.06 newtons. Okay, so I'm going to put that right here. I'm going to call that force vertical, okay, from that tension there, and I'll call the green one here the force horizontal. Okay, now I've accounted for this 35 Newton force, so now I can remove that. I don't
have to have it on there anymore because I've put its two parts on there instead. Okay, so that's going to simplify things for me a little bit. I've now got two forces on there. The other forces acting in this system are, okay, the force of friction. Because we were told there's a coefficient of friction, so there's definitely a force of friction here. We would also have the force of gravity. Okay, and we can calculate that right now. So 25 times 9.81. So that's going to be 245.25. Okay, am I missing a force? Force that might be helpful in finding friction? Normal force, yeah. Now, here's the mistake people make on this question. Is the normal force equal to the force of gravity in this situation? It's not. Why not?
You have a different force acting upwards.
Right. There's an additional force acting upwards. Not all of this 245.25 newtons is pushing on the surface. This much of it is being held by that angled force that I removed. Okay? So how do I get the normal force? Because I need it. I can't calculate friction without it, but I obviously know it's not 245.25. So here's the question you have to ask yourself. Is the box moving vertically? It's not. I specifically said you're dragging it along the surface. So if the box isn't moving vertically, what does that mean for the sum of all the vertical forces? Can you use that to get the force you're missing? Give you a few more minutes on that one. So, I asked you the question, is the box moving vertically? The answer is no. So what's the net force vertically? 0. That means normal force, force vertical, and gravity add up to 0. So that means normal force is 245 minus that much. Okay, that much of the weight is being held basically by that angled force that we erased already. Okay, so to get the normal force, okay, normal force is just going to be 245.25 minus the 9.06. Okay, so that number, okay, minus the full number there. All right, so there's my normal force, 236.19. Now, can I calculate the force of friction? Yes. So now I go back to my force of friction formula. Okay, so force of friction equals mu times the normal force, 0.115 times 236.19. Okay, so 27.16. Ooh, that was close. That's the danger when I just make questions up out of my head. Okay, so 27.16 newtons. Okay, so here's what I have to ask myself now at this point. I've accounted for this. I've accounted for these. Okay, the only forces left are forward and backward. Can I get the net force? Yes. Sorry, yeah. All right, so I'm going to get my net force here. Okay, my net force is going to be 33.8 minus the 27.16. All right, there's my net force, 6.65 newtons. Forward. All right, now to get the acceleration is F net divided by m, So 6.65 divided by 25 kilograms. It's going to be a pretty small acceleration, and that's okay. All right, so our acceleration is going to be to two significant digits here, 0.27 meters per second squared forward. That is probably as tricky as a Newton's second law question will get for you in this course. Okay? In the end, you did have to do a bit of calculating in that one. Okay? There were a lot of forces that we had to find. But the calculating is not the tricky part. The tricky part in that one is recognizing that normal force and gravity are not equal because that angled force had a vertical component to it. And that's the part that people miss. Okay? And guys, I'll be perfectly honest with you. I almost always put a vector nature question like this on the assignment and on your unit exam. Okay? Because this tells me how well can someone visualize a Newton's second law situation and see the forces involved and how they interact to produce the movement. Okay? That's what this question's testing. This question's not testing your math ability. Okay? Yeah, is there more calculation in that question than most of the ones we've done? Sure. Okay? But in the end, what that one's really testing is, could you see all the forces involved and do you understand how they interact? Okay? That's a tricky question. All right? Questions on that one? All right, give that one a try. Back to an incline here. Okay, so you got this one on a 40-degree incline. And we know that the coefficient of friction is 0.185. Okay, so inclined plane, okay, same as any other, it's just this time we'll have to do the normal force. Okay, we know it's a 40-degree incline. Okay, we know it's a 20-kilogram block. Gravity is obviously there. Okay, so Fg will be 196.2 newtons. Okay, this angle's 40 degrees. That side's Fn. That side's F parallel, same as they always are. Okay, and we know that mu in this one is 0.185. Okay, forces involved, F parallel, and friction. Okay, so we got to find all these other forces here. F parallel, as always, sine of 40 degrees times 196.2. Okay, 126.11 newtons. We'll need normal force because we got to calculate friction. Cos of 40 times 196.2. Okay, so 150.30 newtons, and then to calculate the force of friction, mu times the normal force, so 0.185 times 150.30. Okay, so 27.81 newtons. Up the ramp, okay, F parallel we already calculated was 126.11 newtons down the ramp. Okay, net force, vector sum of all forces. Okay, so our 126 minus the force of friction, okay, gives us a net force of 98.3. Divide that by the mass for the acceleration. Should get to two significant digits there, 4.9 meters per second squared down the ramp. Okay, so the good news is adding friction to an inclined plane only adds, a little tiny bit of math. Calculating normal force, calculating friction using mu Fn. Okay, in a question like that one with the block being dragged along, okay, there's a bit more work in one like that. Hey, for sure. Okay, just to give you some ideas here on what we're looking at for coefficients of friction. Some surfaces are really, really sticky, okay, when they go past each other. Like for example, copper on copper is a really high friction situation, okay, where the coefficient of friction is actually greater than 1. Right, that very rarely happens, but if you try and slide copper past copper, it's really, really hard. Okay, but you can see here that in basically every situation, that static friction coefficient is bigger than the kinetic friction coefficient. That's why, again, we don't want to spin our tires if we're trying to get going. Okay, we want them to be in contact and not slip. Okay, if they're spinning, that means the rubber is slipping past the asphalt. Okay, so if we're looking at rubber tire, okay, here on the different situations, so this has to do with, you know, driving safety. Rubber tire on dry asphalt, 1.2, very high coefficient of friction. That's why we use that. Okay, but as soon as you start spinning it, it decreases significantly. Right, if we're looking at on a wet road, it cuts it in half. You have half as much traction on a wet road as you have on a dry road, right? And then once you put it down to concrete, okay, concrete's you know, not as well, it's about the same in terms of the wet stuff, okay, but on ice, look at the number. Okay, and it doesn't really matter whether you're sliding or not. Okay, the coefficient of friction on ice is just stupid low. Okay, which means you can really, really slide a long way. Right, you go from on dry asphalt 1.2 to 0.006. Okay, so like we said, that's why you want to throw weight over top. You can't really control the mu part of it, but if you can make normal force bigger, you're going to have more friction. Okay, it's really about all that we can do in that situation, other than throwing sand on and then having sand and rubber. Okay, they're a little bit better. Sand also helps melt the ice, so okay, that's why we do it. Curling stone on ice, okay, that's why it's so challenging. Okay, the coefficient of friction is pretty low there. Okay, things like that. Okay, not the one I was looking for. Okay, something to talk about. Your tires in the road, okay? We said that the parts of the formula that affect friction are the nature of the two surfaces and how much force there is between them. So why do sports cars have really wide tires versus skinnier tires on other things? Does it make the traction better? Is surface area part of this formula? I don't see surface area in this formula, do you? So why do sports cars have big fat tires? It affects mu. Okay, it's not about surface area. I mean, it's a little bit about contact patch, but it's also about radiating the heat that's produced by spinning the tire. Okay, as you spin the tire, you burn off the rubber, burning rubber. Okay, when you do that, you basically liquefy the rubber and then it combusts and smokes out. Well, if you have a wider patch, then that heat is spread over a greater mass of rubber and it's less likely to get hot enough to burn. And so as a result, you keep that coefficient of friction at a higher number. Once it starts to burn and vulcanize, mu drops. Okay, then the tire is just more likely to spin and spin and spin. Okay, there's a real delicate balance. If you've ever watched drag racing, okay, they'll actually spin the tires and smoke them up real good before they race. The tires have to be warm to an extent in order to have good traction. Cold tires have not as good a traction. But if they get too hot, it goes the other way. There's a real delicate balance, okay, for the temperature of the tires to operate effectively. That's why winter tires work. Okay? How many people have winter tires for their car? Probably getting them off soon. Okay? How are they different? Anybody ever look at them? Okay. Tread pattern's a lot different.
okay, on a winter tire. Okay, on a summer tire, you typically just have, so if we're looking at, here's the tire. If we're looking at a summer tire, you just have blocks. You have traction blocks, and they're all different shapes and things like that, and they just kind of set out. Okay, on a winter tire, you still have traction blocks, but every traction block has these little squiggly lines in it. Okay, next time you're at your car, you can check it out. But your winter tires look a lot different than your summer tires do. Those little squiggly lines are called sipes, right? And their job is to flex when they make contact with the ground and pull water off of the interface between the rubber and the road. All right, so when your tire flattens out against the road, a winter tire is also made of a softer rubber, so it remains pliable. Okay, and so what it'll do is it'll pull that water up, because water is a polar molecule. The hydrogen bonds will allow the water to move up into that sipe and allow the rubber to make direct contact with the road and not have a thin layer of water between instead. That's hydroplaning. That's bad for traction. So your winter tires help to pull that moisture away and allow you to have better traction. In order to do that, they have to have not only those sipes, those little squiggly marks, but they also have to be made out of a softer rubber. Okay? Winter tires are made out of a softer rubber compound. It's why you don't want to drive on winter tires all year. You will wear them out in the summertime. Okay? Because they're softer, they wear way more quickly in warm temperatures. Right? Now, winter tires, okay, made of a softer compound, okay, what temperature, anybody know? Are they affected at? So this is the big argument, right? Is there's two schools of thought. I should always have winter tires. That's the school of thought I'm in. Okay, versus I just need all weather tires or all season tires. Well, here's the difference. Below 5 degrees Celsius, winter tires are pliable. Summer tires are not. They get hard, they stop changing shape, and they are basically just a block sliding along the ice. Okay? Your winter tires below 5 degrees Celsius are going to give you better traction. Even if it's not icy, they're still going to give you better traction because they can take the shape of the road. Okay? I had one day where I really noticed this because one of my tires was just a little bit low, and I hadn't changed my summer tires over yet, and it got really cold. And when I got in my truck and drove away, the truck went thump, 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 because the bottom of the tires had gotten hard in a flattened position. So there was like a flat spot on each tire until I got the tires warmed up from driving enough that it kind of lost that shape. Okay? It was like literally flat on one side. Okay? It just, for whatever reason, it's just freak occurrence. It was like 5 degrees and then it just all of a sudden dropped. It was like -30 in the afternoon. Okay? And so that actually didn't happen. Right? So what you want is tires that remain pliable in cold temperatures. But that means don't be on them in July. I always laugh when I'm at in a parking lot and I see somebody still got their winter tires on in July because I just know they're shredding them. Okay? They're so soft that they're just wearing like crazy. Right? So they can help. There's good science behind them. Yes, it's an extra expense for sure. It's another set of tires, but there's science behind it, and that science does work. You do get better traction if you have winter tires, especially in really cold temperatures. Okay. All right. I have time for one more here. Okay, this one's a little easier than the one we did with the angled force. This one doesn't have an angled force. Okay, but it does have a coefficient of friction. So 20 kilogram box on a level surface, okay, being pulled by a 200 Newton force. Okay, coefficient of friction is 0.8. Want the acceleration of the box. Okay, let's walk our way through this one here. So we got the 20 kilogram box. We know that there's a force forwards of 200 Newtons. Okay, we know there's a force of friction backwards, but we don't know what it is yet. And of course we know that there's a force of gravity here, and that's going to be 196.2 newtons. What's our normal force in this situation? Josh, what's the normal force in this situation? 196.2, right? In this situation, they're equal because I'm not trying to lift the box at all. Okay, all of its weight is sitting on the surface. So
So in this situation, okay, they are in fact equal. Since I know that, I can calculate the force of friction. It's just mu times the normal force. Okay, we know that mu is 0.800, so times 196.2. All right, so we're looking at friction being 156.96 newtons. Okay, acting backwards, vector sum of all forces. So F net 200 minus the 156.96. Okay, so our net force is 43.04 newtons. And then our acceleration will be our net force divided by mass. 43.04, okay, divided by 150, or sorry, by 20. All right, so acceleration will be to too significant, 2.2 meters per second squared. Forward. All right, so you know, Friday's quiz will not involve any coefficient of friction questions. Okay, Friday's quiz is strictly going to be Newton's second law up to what we did yesterday. All right, but as of today, we're done with Newton's second law. Tomorrow you're going to do your assignment on Newton's second law. Friday quiz on Newton's second law. Next week we start Newton's third law, which takes like a day, and then we're moving on to work and energy. So we're about half done. I'll probably be telling you when your unit exam will be sometime next week. I'll be telling you sometime next week. It isn't sometime next week. I'll be telling you when it is sometime next week, just so there's no confusion. Okay, good work today, guys.